Over the past month, I've been working on an 8286 breadboard-based system just to learn a bit more about the 286 processor. I'm coming from more of a 6502 and 65816 type of experiences, having started with some of Ben Eater's 6502 work and maybe prior to that his 8-bit computer. I'm a hobbyist. I enjoy doing this stuff, and I thought I would maybe share my experience of learning this 286 as I go through it. And I'm providing this video just kind of as an update. So if you've been watching my video series, I don't know if you're going to see anything too new or exciting in this video. But for those of you that maybe haven't been following my YouTube series and are interested in a quick update of where I'm at in my build, this would be a good video to go through and catch up on some of that. The specific processor that I am using is a Harris 286, and I'm actually using the -25, so the processor will be capable of going far faster than I'll be able to get it to run, especially in a breadboard environment. This is what I'm using. It comes in a package that looks like this. So this is a PLCC, it's a 68-pin PLCC package. And that obviously is not very breadboard friendly, so I spun up a little PCB that just simply converts that PLCC format into a couple of breadboard rails that I could tap into a breadboard and start building out a system around it. As I was doing my initial reading on the 286, this is a graphic that's provided in the Harris documentation for the 286. And pretty much any data sheet for the 286 or any of the books that you'll find will show something comparable to this. So this helped me kind of see that, okay, I've got this processor here, the ADC 286, and there's all these other chips around it. I didn't really want to try to track down these chips like a clock generator and bus controller and all of these things that seemed really Intel specific. So I thought I would just kind of wing it and build a system up around it. And that's what I did. I started with this, and I'm going to call this build number 1. And you can see my processor there, and I put some bar graphs around it to show the addressing and the data coming out of it. I've got some other LEDs that show me other indicators that are really important, like this S1, S0, there's a COD int A signal, etc. that I had to learn how to use. I didn't know how these functioned. I had a little utility PCB that helped me do clock and reset, and I used that for my clock source, and just started connecting into this and understanding what I could do with it, starting with something as simple as just hard coding some NOPs or non-operations and see if the processor would even read that, and could I work with the processor. Eventually I worked my way up to this build, and you can see there's wires everywhere. And maybe to point out some things here, let me pull up the pin. So to start out, I've got the processor sitting here, and that processor is sending out all these data lines down to, this is my flash memory down here. And the way it works with the 286 is it's expecting to read 2 bytes of data at once, a high byte and a low byte, or a most significant, least significant byte. So I have one flash chip that's my high byte. I have another flash chip that is the low byte. And so when I go to an address and try to read, I'm going to read 2 bytes, one from each chip at the same time. Same thing over here for the RAM. I've got a high RAM, I've got a low RAM. I've got this little device which is called a PSOC, and that is doing, in the case of this build, it's doing my address decoding and also some additional logic of when I'm doing reads and writes and things like that, whether it's to memory or to I/O. And I'll talk about that a little bit more later. I have just a little power distributor up here that I'm using just to simply give power to different parts of the system, like I connect out and connect to the breadboard here through like 10 pins, just so I've got a nice solid power connection. And then I jumper power over to my reset clock, and I also jumper it over to this, what I'm going to call a bus board. This bus board is just an extra board I had sitting around. I had designed quite a while ago when I was working on my own 16-bit processor. And in the early stages, I just needed something to be able to easily distribute a bunch of address and data lines And that actually came in handy here. I thought, well, I'll just tap into it. So in addition to my address coming out here and my data lines coming out here to all of this, I also ran address and data to this bus board. So then I could tap into any one of these headers and get to all of the addresses. And you can kind of see here I scribbled on the board how I'm using this specific version of it for this build. And up top I put in some bar graphs, LED bar graphs, so I could kind of see what's going on. I've got an Arduino Mega over here for debugging. And I eventually got to the point where I put in some bar graphs over here just to write I/O out of the processor and see if I could manipulate an I/O port. And then I also got to the point of putting in a 2-line LCD, a 1602 LCD. And all of that is going through, basically I put in some latches down here and a transceiver so that I could get data out and read data back, for example, from the LCD. And I got that up and running, and that was working, and that was great. So then I was trying to figure out what's the next step. Well, the next step for me was then to go back to this diagram and say, well, what if I actually implemented it as Intel has it, the basic architecture laid out here. Because in my build number 1, I was using my PSOC, and this PSOC up here really was doing a lot of the things that the bus controller would do, and maybe even some of the things that this clock generator would do. And I wasn't using latches or transceivers or anything like that. So my goal then is to say, okay, how can I build a system and leverage these basic chips? So I've got the 286, I've got to go get a 284 clock generator and a 288 bus controller and figure out what I'm going to do for latches and transceivers because the ones that are listed here are not really easy to get a hold of. So what could I use in their place? And at some point, could I do an interrupt controller and other things that I'm going to want to put into my system? And also as part of this, reduce the requirement of having this PSOC. It's just a nice, convenient way to do decoding and other things. And inside of it, I'm really just using gates, standard logic gates. So there's nothing fancy about it. It's just an easy way for me to do things that are happening in other parts of the system. But I kind of eventually want to pull that PSOC out and really use everything from the era of when this system really was being built. Another diagram I found showed that typically you would connect your memory, ROM, RAM, whatever it might be, outside of these latches and transceivers and things like that. And that's not how I built system number 1. So I thought, okay, let's give this a shot. So I did a little bit of work on just planning. So I said, okay, I'm going to start out with a footprint of 8 breadboards. And you can see over here I've got this board that you don't see the processor. It's actually a 2-stacked. It's a double layer board. Well, double layer is a bad way to say it. There's 2 boards here that stack, and the lower board actually holds the CPU, and the upper board hosts a bunch of LEDs just to show status. And I'll show more about that here coming up. I then created some PCBs just to easily distribute power across all these breadboards. And then I put in one of these bus boards that I had, and I just started working my way through the chips. And so there's a clock generator. You probably can't read the text on this, it's really small, but there's a clock generator chip that's part of the standard Intel design. There's an interrupt controller, a bus controller, a bunch of latches, some transceivers, ROM, RAM, this PSOC device that I'm using to do address decoding, an Arduino debugger, there's a coprocessor, and then I can get over into these programmable peripheral interfaces, or PPIs, that allow me to do I/O out to other devices. And I thought with one of those I could then do things like a keyboard, a small LCD, maybe eventually do some SPI communication, things like that. So that was just me thinking through what this might look like. And then I got into actually building this. And what I'm going to do now is just kind of show you where I am today. I'm not done by any means, but I'm at a pretty good milestone. I'm happy with the progress that I've made over the last 4 weeks. And as I've been going over the last 4 weeks, I've been publishing to a playlist on my YouTube channel. And it's basically an 8286 build playlist. And I think right now there's maybe 34 videos, or low 30s as far as how many videos I've posted. So kind of averaging one a day, I would say, over the last month, and just showing what I'm doing, what I'm learning as I go. By no means is it a recipe for success. I'm learning along the way. I'm finding things I should have done differently, and that's just part of learning. But if you're interested, I've got a lot of content out there that talks about each of the steps I'm taking. And if at any point you want to know more about something, just reach out to me. So some of the first videos were part of this build number 1, I'm going to call it. And I got into connecting up memory, like flash memory, and then I got into actually running some code. And when I build code, I'm brand new to x86 assembly, so there's definitely some stumbling there that I've been going through, just trying to learn that. And I've got to then take my code that I build, and I've got to assemble it and split it into the high and the low ROM and get that into the system. And I've worked through that in this first series of videos. Then I got my RAM connected. I put in some decode logic in this PSOC. Initially, I was starting with separate 7400 series chips, and I just kept changing things all the time, and I was getting really tired of just moving wires and chips around all the time. So I moved to this PSOC, which has been wonderful. Then I did some output to LED bar graphs, and then I eventually connected an LCD. And then beyond that, I not just wrote to the LCD at a slower speed, I then updated my system to read the busy flag on the LCD, and I was running the processor at 5 megahertz. So that was great, and it was a very messy build, wires everywhere, I guess maybe as you would expect for a breadboard build. Then I continued, I improved some of the power distribution, I got in this bus board in the middle of the system, or connected to the side of that system. I hooked up an Arduino to do basically to act as a logic analyzer or a debugger that I could use, and that was all good. Then I got to episode 13, and I laid out maybe some thoughts on starting a new build, which I'm calling build number 2. And then I start progressing through that build, and I talk about the basics of building this wooden baseboard platform that everything is sitting on top of. I got into some of the chips that I was going to use from the Intel design. And then I went through each of those chips one by one. So I went through the clock generator, the bus controller, the interrupt controller, the math coprocessor, and all of those were without actually hooking anything up because I didn't have most of these chips at the time. So it was really just reading the documentation, putting together a schematic, and at least in theory, how I thought it was going to hook up. And along the way, I caught some mistakes. Others helped me catch some mistakes as I went, which was great, having everybody give me feedback. Then I eventually got into the PPI, Programmable Peripheral Interface. Then I made an updated PCB for the processor that included a hat. The hat is that top layer board, that upper board. And actually, I had some of my wires transposed in the schematic. So while it worked, it just wasn't convenient because the LEDs were in the wrong spot. So I went without the hat for quite a while. And I got into just wiring up the system, and I worked my way through that. And along the way, maybe experimented with what a PCB could start to look like. I got my bus wired in. I got the ROM and RAM in and up and running. I then got into episode 30 here, where I was doing some tidying up or really cleanup of the system, and that was really helpful, that cleanup that I did. And then I continued to improve my Arduino functionality. I connected some of these PPIs in a 1602 LCD, and then I went through the assembly that I'm using to drive that. And as part of that, showing that the system is running at a full 8 megahertz as far as the processor clock is concerned. And that kind of gets me up to where I'm at today. So this is what it looks like today, and the system is running at 8 megahertz. And let me just take a little time and walk through this if you're interested. To start, in the upper left, this is a board I built during the process of this 286 build to consolidate my power distribution board and my clock and reset board. So I've now got a single board. This board is great. I'm really liking it. And basically it allows me to bring in power either through a barrel connector, one of these quick connectors, or instead of a quick connector, I could put like a blade screw terminal type connector, or banana connectors. And I really like the banana connectors. So I go straight from my DC power benchtop power supply, basically, that's sitting off to the side. You can't see it over here. And I bring then straight from that with banana plugs, banana cables into these two plugs here. And this little corner is just input values, and you'll see later in the video that just this LED will be on, showing that I've got power coming in, but then I've got a separate LED that shows I'm sending power out to the rest of the system. And I thought I'd put a relay in and a switch so I can turn on and off the system with that switch and really have appropriately sized traces to distribute power out of this board. And so as far as power is concerned, you know, I've got one plug, I've got another terminal connector over here, I've got this one here. But basically this gets power down to here. It also gets me power, you can't see it, but it's run over to the right and up into this rail it's soldered in. And then I've got another one that then comes down to this rail here. So I've got 3 solid connections for power, and then these rails run power all the way down through all those breadboards, which is great. When I connected the breadboards, I actually left an intentional gap the way I designed this, just on the spacing, and that gap has been really nice too, just because it gives me some room to run wires back and forth and not cover up the power. So that's all actually played out pretty well. So then if I look at this, right here is where my processor sits, and this is what it looks like as far as the hat is concerned when it's on. But then if I take that hat off, this is what's sitting underneath it. And somehow my image got reversed, but just mirror that image, it's backwards for some reason. I think when I resized it, maybe I flipped it. But anyways, you've got the processor on the lower PCB that plugs in with basically pin headers into the breadboard, so they're long and go all the way through that board, plus expose this so that the top can connect into it. So this top board right here has its pins that drop down into here, which is great. So you don't see the processor anymore to the right. It's kind of hidden, but it's within this little assembly right here. And if I look at the hat, basically what I'm showing here is these are LEDs. You probably can't see this red very well, but right up here I've got all these LEDs that will show me the value that's on the address bus. I shouldn't say address bus, but the address values coming out of the processor. And then I also show all the data values, and then I show a series of control values that are important to understand as I'm debugging and working with the system. Then after I have that in, I then come up here and I put in a clock generator. I have the bus controller. I then have my addresses all coming down here to, down here I have my transceivers. Sorry, not transceivers, latches. See if I can find a color that'll stick out no matter what. So I've got 3 latches. Basically each of those is latching 8 of my address lines. And then once they're latched, they're put onto this bus board that I can then distribute across the rest of the system. Same thing for the data. I bring the data into a pair of latches, or not latches, sorry, these are transceivers. And then after those transceivers, they go onto the bus board. So 3 latches and a pair of transceivers gets me all of my address and data lines onto this bus board you see in the center. I have one more latch that is for certain control signals, and so I do have some control signals being latched and sent out to the rest of the system. I have not yet connected, this right here is my interrupt controller, and I have a math coprocessor down here that will at some point hopefully be functional, but they are not connected yet. On my bus board then, I've got these bar graphs up top, and those bar graphs are showing me the values of addresses and data lines that have been latched. So this processor through the bus controller is going to give me a signal of when I should latch that stuff. And I shouldn't say latch for the data, it's just the address lines that are being latched, but the latched address lines and the current data values coming through the transceivers are being shown up here. And I'm going to go ahead and clear everything on the slide for a minute. Then as I was going through this, something else I wanted to be very careful with was these connections. For example, they're all connecting into the breadboard down here. What I actually did is I designed a little PCB, and I've got a few different flavors of it, but it allows me to connect in pin headers, solder in pin headers into the PCB, and then solder in the wires, and then that whole thing can click into the breadboard. That'll prevent any single wire from pulling up and out of this, and those have been also awesome to have. So I can cut them to the right length. I've got a 2-row version, a 3-row version, a 4-row version, and a much longer version that lets me connect between 2 different breadboards, and I also have a shorter version that lets me connect between 2 halves of a breadboard. So those have been really handy. So you can see then I bring all the stuff into these transceivers and latches, and then I bring it over to the breadboard with a really, again, solid connection. So I'm using a soldered wire onto a little PCB with pin headers that then connects into the pins on the board. So I can disconnect this relatively easily and pull that board out if I had to, or do something different with it. Then I continued my build, and I did add an Arduino debugger up here in the upper right, and all of its wires are using these little adapters. I just grabbed some Cat5 cable because I wanted some thinner wire. I didn't want it to be as bulky, and I had it conveniently laying around, so I pulled out some Cat5 wire. It's listed as 24 gauge, but it doesn't measure 24 gauge. It's probably closer to 26 or 27 gauge, so we'll just call it 26 gauge. All the rest of the wires that you see throughout this build are going to be 22 gauge. So this type of wire down here would be a 22, and all solid core. But I tapped that then into the bus board, and then I can use that to debug. And the debugger I've written is actually pretty good at this point. It reads out address and data and all these control signals, and lets me kind of see what's happening on my terminal screen as the system is running. Then I continued over to the right, and I took this bus connection and basically ran it to another set of PCBs that click into the breadboard here, which gave me a whole bunch of pins that I could then distribute to other chips. And hidden, you cannot see it, but there are a pair of RAM chips here. And so I got my RAM chips and all my addresses and data lines run to that. I then came in and put in my flash ROM, and I've got the low and high byte for that. I then came in with these programmable peripheral interfaces, or PPIs. This one here is going to eventually host a PS2 keyboard, and I've got the chips set down, but I've not started actually hooking that up. That'll be in an upcoming video. And then this one up here is actually going to be controlling this LCD. And the LCD is working, and at the moment I have a 32 megahertz oscillator put into this clock card. And coming out of that clock card, I have a flip-flop, a 7474, that then sends the signal out of it, and just so that I have a clock and an inverted clock that are nice and crisp and really synced up. But when you do that, that pulls that speed in half. So I have a 16 megahertz clock coming into, I think it's right here. So I've got a 16 megahertz clock coming in. And the way the 286 works is within it, it's going to use half that speed, what they call a processor clock, or P clock. So this processor is running at 8 megahertz. And this LCD I've got programmed, and it is running well at the full 8 megahertz for the bus system, or for the entire system, I should say. And that's kind of where I'm at. So next steps, I need to get my keyboard circuit hooked up. I need to be able to support interrupts through this interrupt controller. And I've got probably quite a bit of work to get that going. And then after that, I probably will try to get this math coprocessor running, and then get maybe some basic program where I could enter in a couple of decimal numbers and have it do a multiplication or something like that, leveraging the coprocessor. So that might be a pretty fun test to see if I can get that far. Beyond that, I probably am going to add support for SPI, to do SPI communication, and I'm going to try to do that through one of these PPIs. And then maybe I could eventually connect, let's say, an SPI LCD screen, a higher res, like a 320 by 200 or 240 or something like that. And I do want to eventually add an actual ISA slot or two, and actually follow the ISA spec for the most part, or a subset of it. And that way I can add in, I have a video card that I've built for previous systems. I wouldn't mind maybe tweaking it, adjusting it so that I could plug it into this and use ISA to run a 320 by 200 or 240 by something, 240 by 200, whatever the resolution I end up picking, but run something that could drive an actual LCD external monitor type of setup. I have another card that I wouldn't mind porting over to this, which is a sound card. So I could go through and try to get that running. That actually has its own 65816 processor running on it to drive the processor, or to drive the sound processing on that system. Think of it as a sound coprocessor. So it might be pretty neat to get those two things plugged in, and then maybe I could get a mouse plugged in, and there's other things that I could work on as I go. Right now, my biggest hurdle is probably just learning more x86 assembly, and I have a lot of work to do there, so we'll see how that all goes. If you want more information, do take a look at my YouTube channel, and also I have a blog where I try to just add some additional information, whether it's schematics or design files or just other commentary that I might not have included in the video. And often if I get follow-up questions, I'll often post stuff on my blog about answering whatever those questions are so others can use the answers. So here's the system. It is currently off. I go ahead and I just flip it on with the switch. Right now the clock card is set to run off of a 555 based timer, so it's a pretty slow clock, and I'm doing that intentionally so I can debug. And you will see that on the hat of the processor, you can see it's showing me my address and data values. Again, the address is before the latch, so if you compare that to the address value on the bus board, it might be slightly different, either ahead or showing something different that is not meant to be latched. And so there are some values the processor is kicking out that are not latched, like there you saw it flip all ones for the address. Here I'm just turning up the 555 base timer to be a little bit faster. I can have that go up to, the way it sits, up to about 2000 hertz or 2 kilohertz, which is plenty fast because the intention there is to use it for debugging. But then here I could log to the Arduino and I could see what's going on as far as all the signals. That logger is actually decoding when I read an instruction. It decodes what instruction is being read, and it shows me in the log output, you just ran whatever, an in and out, something that you're doing with a move, whatever it might be. But it kind of helps me just to learn, and as I write my assembly code, figure out where I'm making mistakes and fix it. So this is pretty handy. And you can see it's all the way up to the H on the screen, and I can turn it up a little bit more and let it run as fast as it will at that 2 kilohertz, and now you can see it writing out Ola and going to the second line. Now I can, on that hat, if I don't want to use those LEDs or the LEDs on the bus board, I have jumpers on those that I can just pull the jumper, and it basically disables those outputs. So later when I'm running at full speed, those LEDs are pointless, and I can just pull the jumper and they'll turn off. And here I just turned off the system and turned it back on, running with the full oscillator, and you saw that it instantly pulled up that LCD output, because basically at 8 megahertz it rips through that really quickly. So that's the current state of my system. If any of you have questions or feedback, feel free to reach out to me either on my blog or my YouTube channel. I've got an email address posted on my blog website, or my website that blog is within. Would love to hear from you, and look for more updates as I continue to build this out. Eventually I would like to get to a full PCB version of this with ISA slots and a couple add-in cards. But that's going to take a while, and we'll see how it goes. So thanks for watching.